Okay, POE students, we're going to talk about material testing. So make sure you get your engineering notebooks out, and here we go. So, for material testing, what is it? We're going to test the material, see how it's doing. Okay, there's static testing. That's when you have a constant load or you just keep stressing it and stressing it. In this case, pulling it apart is the one that we're going to do. There's also dynamic testing, and that's when you have varying load conditions like magnitude, cycling. So you do it, then you back off and do it again and back off, and you deal with the mode and things like that. We're only going to worry primarily with static testing. Okay. So, what are we looking for? Strength, how it deforms itself or deformation, fracture, and some design requirement compliance that we have to meet to be able to do this. Okay. The three standardized tests that there are is tensile, compression, and hardness. We're primarily going to focus on tensile test, but we will mention compression and hardness later on. Okay, so a tensile test is a straight line test, usually on the y-axis, which means up and down. Okay, here's a machine that does that going left and right. This is a machine that does it going up and down. It is destructive, which means the thing that we will test will be broken by the time we're done. Okay, that's a destructive type of test. So we're going to call this thing a dog bone. Kind of looks like a dog bone there that you give your dog. Okay. You've got thick ends, and then it's thin and uniform diameter throughout the middle part. So we're going to hook this into a machine here, and then we're going to start pulling it apart with a whole bunch of force. Okay. So here it is inside of a machine. Um, the dog bone is being clamped in between this jaw, the jaws at the top and the jaws at the bottom. You can also do it with screws, okay? But you need to know the length, especially the length of the middle part and also the diameter, okay? So this dimension drawing gives you other dimensions, but primarily it's the metal length right there and the diameter of it that we have right there. Okay, so let's take a look at a little video, hooking one of these up and seeing what we can do and seeing what it looks like.
Conducting tensile test, 500 diameter tensile specimen, stainless steel material.
So they're putting it in the machine right now. Tightening it up.
Engage tensile specimen between crossheads.
Hooking up the sensor to it.
Apply extensometer to determine yield strength of material.
One type of sensor. And primarily, you're going to look at that screen that's to the right. Kind of hard to watch both things, but what they're doing, they're getting a yield strength right now with that test reading. But that's not the actual test that they do on it.
After yield strength has been determined, remove extensometer and continue test to failure.
So now they start to pull it apart. Okay? Not real exciting right here. It's kind of like watching paint dry, but that's what it is. Now, carefully watch in the middle of that dog bone, and you'll see the middle kind of suck up a little bit, or looks like it's denting in. You can really see it right there. That is called necking. And then boom, it broke off. So it is a destructive force. They just wasted that dog bone on that type of strength there for the material that it is. Now it's stainless steel, so here he goes to check the length of it. Electronic caliper there, and he's checking the width of it right there. Okay. So that's what's going on when he's doing that. Okay. Now I've got a little shorter one. This one deals with a rebar. Same type of video. This one only lasts 30 seconds. So remember, the rebar, usually made of iron, we'll get past the ad here. So again, guy's going to put it in there, attach it to the top and the bottom so he can actually pull it. Fancy one, they've got readings here, but watch as it pulls it apart. You can see the graph there. We'll talk about the graph in just a moment. You don't see nearly a lot or as much necking going on when he pulls it apart. So, boom, there it was. Okay. Now, there are other videos out there. You can go and take a look if you'd like to see what the other ones are. They're kind of fun to watch. Some really stretch and have a long neck. Some have none, like this one. And we'll talk about that. Okay. So, we're going to talk about the tensile force is applied to the dog bone. And then we're going to deal with the dog bone elongation of it. Okay. And we get this type of graph where you have the force, the more it bends. And then you've got this type of graph that shows you the delta or the bone elongation on it. Okay. So if we have two different samples here, same material, both 230 red brass, one's got a different diameter than the other one. Will the applied force, tension, elongation be the same for both? No. How come? Because they have different diameters. Okay. Just like a 2x2 and a 4x4. 4x4 is going to have a lot more material to deal with. Larger sample indicates a larger load. Can you manipulate the material and not the individual? Not really. Okay, so you need to write this down. Stress, what is it? It's the load per unit area. Or stress, which is the word stress, the symbol is the sigma, which is like a little O with the tail on it. That equals force divided by area. Okay, the force that we're going to have is provided by that machine there that we had. Area we already know. So calculate the stress of a dog bone with a 430-pound applied force. Well, the dog bone's got an area of a circle, pi r squared. This is the diameter, so we have to take half of that in our formula, and we get an area of about 0.0123 square inches. Now I can figure out the sigma of it. Take 430 divided by the area, and you get about 35,000 psi. I say about because of significant figures and things like that. If you do all the math on your calculator, I'd be happy with that, or we can do significant figures. Okay, that's the stress. Okay, then we also have something else called the strain. That's the amount of stretch per unit length. Okay, so you have to figure how long it was stretching divided by the original length. And that looks like that little E right there. Okay, that's the epsilon, capital epsilon. Little e still is epsilon, but it's a different one. So they're using the big E here, and we're taking the delta or the change in length under that load as it's pulled apart divided by the original length. Okay, so here's our dog bone. We know the original length is 1, so L sub 0 is 1, and we know it elongated to 0.0625. That's how much it's stretched, or the total length would be 1.0625. Do a little bit of math on it to get epsilon, and that turns out to be 0.0625. Not a lot of hard math on that one. Okay? But it's the elongation divided by the original length. Then you look at here's your graph of stress versus strain. Okay? So the initial response is linear. That portion right there. They're proportional to one another. That's also called the elastic range or the proportional limit. It's proportional because it's got the same slope throughout that entire thing. Okay? Modulus elasticity. We've talked about that. That's the proportional constant or the ratio of stress to strain. So that's why we did those two formulas earlier, and you get modulus of elasticity, capital E, normal looking E, is sigma divided by epsilon, or stress divided by strain gives you modulus of elasticity. Okay, a little different than the other ones that we did when we were doing centroids and things like that. Okay, remember, modulus elasticity is the measure of your stiffness or the ability to resist stretching when it's loaded. And that's what we did. We stretched that dog bone that we had in there. And it's different for every material that we have. Okay, if the load is removed, the test sample goes back to normal shape. Okay, but anytime after that linear part, it's going to be deformed. Okay, and that's where the necking occurs when you go through and do that. The elastic limit is at the end of that linear line right there. Okay. The elastic and proportional limit are almost the same. Elastic limit is just a tad bit beyond it. For this class, it's going to be the exact same thing. So you don't have to worry about that. Resilience, the amount of energy per unit volume that a material can absorb while in the elastic range. It's the area under the stress or strain curve. So what's that area look like? Well, it's a linear equation. The hypotenuse is linear. That's going to be a right triangle. And the area of a right triangle is half the base times its height. That's the resilience. Why is this so important? Well, you're in a fender bender. You got a car bumper. Don't you want it to go back to the way it was supposed to look? Otherwise, you got an expensive accident that just happened right there. And it doesn't take much of a push, but just a little bit of a nudge, and you can have a lot of damage that doesn't go back to normal. But the resilience is the area that you have underneath that curve there, underneath that linear portion, not the curve. The yield point, any point after that, produces more strain and more stress. Okay, it's not a well-defined point. It's just kind of an eyeball. Just take a look at it. But anything beyond that point, and you're going to have some deformation. Okay, and that's what anything that occurs in this curved area here is called the plastic deformation. When the load is removed, it doesn't recover. Okay, and then you've got failure at the end to be able to figure that out. So deformation on your test sample there, your cross-sectional area decreases, but it's still holding on tight. Okay. But it's still able to hold the load because you're deforming it now. Is the material getting stronger? Yes. Internally, they're grabbing onto one another to be able to go through and do that. Okay. Then the weakest point is stretched, and it becomes so long, then it goes pop, and you're done. Okay. The new, when it's done, it's done. Okay. But each new point stretches a little bit and a little bit more. Okay. The tensile strength is the actual maximum amount you'd have there. Okay. That'd be like the vertex of a parabola. Okay. The weakest location at the point continues to decrease in that area. You can see the necking going on here. Yeah, get your little funnies out. Yeah, necking. We're talking about it. But that's kind of what it really looks like over here in that picture. It looks like a neck, and you're stretching it. But that is the tensile strength, is the maximum that you have right here. And then the failure at the end, and that's when it pops. And you do hear a little pop going on. So that rebar didn't have much of a neck, didn't have a lot of plasticity in it. Okay. The greater the ductility, the more the material can be deformed. So that iron piece doesn't have it very much. Okay. So we got 3 samples here. You can see the most necking on the left, less in the middle, and very little necking right here. Okay. Then we're talking about brittleness. The one on the right would be the most brittle because it just, boom, cracked right away. Where this one, the pieces started to grab onto one another and you had the necking occur. Okay. Now, what do we look at this? Well, they both have the same maximum amount. Both have the same tensile strength, but the one on the right is a lot more brittle. Okay. It doesn't have as much strain. So you've got different types of metals that will do that. Brass, stainless steel. That first video was stainless steel. So it was actually necking pretty good. The second one was made of iron. It had no neck. It almost broke right away. So you've got different materials have different things there. Toughness is the total area under the stress and strain curve. Now, to actually do that area underneath this curve, you'd have to do a little bit of calculus. We don't get into that type of math, okay? But you would later on. That's when we talk about toughness being the work per unit volume when we go through and do that, or the area underneath the whole thing, okay? Now, compression test, the same thing, except we're not pulling them apart. We're kind of pushing them together. But the same thing is going to be almost similar to it when we do the compression test. Think of a concrete would have a compression test. So bridges, you would have to have a compression test. If the bridge failed, you check the concrete. Okay, maybe they put too much water in, not enough sand. There's a whole lot of things that could go on when you go through and do that. And then you've got a hardness test. Here, you're going to ding it a little bit, 500-pound force for 15 seconds, and the resulting crater or the dent in it, then you measure it and compare it with the other one. That's called the hardness testing. I won't test you on that one. Okay? Same with the Rockwell test. This one's a diamond tip cone is forced to the sample, determine the depth that's measured from that force of the diamond tip cone. Again, we're not going to do that. We're just going to stick with the tensile strength and the stress and the strain curve. Okay? And that's all we have for notes going on today. So good luck. You've got a little worksheet to go on after this. Other than that, we are done. Have a good
Meet
day.
Suvi, the magical all-in-one countertop kitchen robot.